Hello and welcome to MOOC on optical communications. We will continue the discussion of optical amplifiers. We will look at couple of aspects that make erbium doped fibers not very ideal when you would actually expect it to be an ideal amplifier. Okay. The first thing is, if you were to look at the gain of the erbium doped fiber amplifier, so you are looking at an erbium doped fiber amplifier, you would actually expect a very flat gain. So over its operating wavelength, you would expect it to have a flat gain. Why is this flat gain important? Let us assume that you actually come in with the input signal actually happens to be two wavelengths, okay, one wavelength at some lambda 1 and other one at lambda 2, but the power of lambda 1 is P1, power of lambda 2 is P2, and we have assumed in this particular case that P2 is higher than P1. Of course, information is sitting on these two wavelengths, these are the two carriers with which you are coming in. If you had a flat gain erbium doped fiber, then the output would exactly be G times P1 for the wavelength lambda 1, and then you had G times P2 for the wavelength lambda 2. However, because erbium doped fiber amplifier gain actually depends on the wavelength, it turns out that the gain that you are going to get for P1 will be different than the gain that you are going to get for wavelength lambda 2. And in case this gain happens to be much larger than this particular gain, it might so happen then that this fellow will eat up all the gain of the erbium doped fiber amplifier, whatever that it could give, and then the available gain for other wavelengths would be very small. Okay. This is a problem that is very pronounced in a semiconductor optical amplifier. In semiconductor optical amplifier, this actually happens, leading to in fact loss of a certain signal. Okay. Instead of a gain, your actual signal might simply disappear because one of the signals occupies the entire gain. That problem is not so severe in erbium doped fiber amplifier, but it still leads to a little bit of a problem in the sense, not a little bit, and the problem in the sense that signals which are at different wavelengths experience different gains. Okay. So you can't really assume that all the wavelengths that are coming in will be amplified with the same gain. The situation becomes little worse when you actually come in with two different wavelengths having equal powers. Okay. So if you come in with a lambda 1 at a certain power P and lambda 2 also at a certain power P, and you have certain other component after the erbium doped fiber, but the output signal that you are going to get will be G1 times P for lambda 1 and then G2 times P for lambda 2. So notice that although at the input side both lambda 1 and lambda 2 had equal powers, okay, the output powers are not really equal. So you really want a certain flat gain so that this large changes in the or the fluctuations in the wavelength powers are to be avoided. Unfortunately, erbium doped fiber does not provide a flat gain, rather what it provides is a gain that is function of wavelength. So if you were to look at the gain function somewhere around 1520 to 1600 closely, you would see that the gain function goes something like this, and the situation becomes slightly more worse. Okay. So here this should have actually gone to slightly onto the longer side. So anyway, I am not actually drawing the exact curve out here, but this is what would typically happen. The gain curve would actually start to change as the pump power starts to increase. So the gain is not just the function of the wavelength, gain has also become the function of the pump power. So because of this problem, what will happen is the gain at different wavelengths are not exactly the same. Okay. And if you were to put this amplifier to make a laser, then if you do not control the frequency of the laser that is coming out, then much of the laser happens in this particular wavelength. So if you were to construct a mode lock laser using an erbium doped fiber, this is something that you are going to see. It would mostly laze in this particular window, which is around 1550 to 1560. Okay. So this gain not being flat is an important problem, and there are solutions for that. One solution would be to replace the silica fiber with a different fiber such as a fluoride fiber. Okay. There are solutions available with this one, but these are not widely used. Rather, we use what is called as a long period grating. If you remember the discussion on the optical devices, a long period grating was a device which actually coupled the modes of a core and the cladding. Okay. What was the reason why we used a long period grating, or at least I mentioned that we used long period gratings, was the gain equalization for a erbium doped fiber. It is possible to fabricate a long period grating whose transmission spectrum, say T of lambda, will be in such a way that G of lambda coming from the erbium doped fiber and T of lambda coming from the long period grating together can be made to be uniform, which means that if the erbium doped fiber gain is non-flat and then has a certain spectral distribution that would look like this, okay, you can actually make a long period grating with a spectrum that would be kind of inverse to this. Okay, I probably have not captured this correctly, such that their products actually will give rise to more or less flat spectrum, okay, flat gain spectrum. So gain will essentially, overall gain G overall will be more or less equal to 1 for this particular thing. So such a major use of a long period grating that commercial erbium doped fiber amplifiers operating over this wavelength actually come with a LPG integrated to that. So you have a fiber, then you also have an LPG, and then you have additional components that go into the fiber. If you look at a commercial erbium doped fiber amplifier, what you actually see is you need a pump coupler, okay, and you need a pump. What is the wavelength of the pump that is normally used? 980 nanometer. You have a signal that is coming in which is at around 1550 nanometer, and this would go into the fiber. Okay, so this is your erbium doped fiber, but not the entire pump would be utilized. Some part of the pump might still be available to you, so that forms the residual pump, and after this you normally put in an isolator. If you want to make an equalizer, then you also put in a long period grating up at this point, okay, and then you also put one more erbium doped fiber just to symmetrize the whole thing, but this is essentially what you are going to see in a commercial erbium doped fiber amplifier for broadband application. Okay. There are a couple of things on which the gain depends. We have already seen that the gain kind of increases with the pump power that is input, right. So however, is it possible that I can just keep on increasing the pump power so that the gain keeps on increasing? Unfortunately no. The reason why it does not happen is because a larger number of the pump photons coming in means that these signals are getting excited, okay. However, they will also start to decrease back, okay. So there is some sort of a saturation that really happens when you start putting in large amount of pump power. This saturation is even more pronounced when you actually have a signal to this, okay. Initially the gain of the signal starts to increase and then the gain starts to saturate, okay. The gain basically saturates with the increasing input power. Why is that so? Well, initially when the input power is here and then you have created a population inversion, then there is a chance for these input photons, the signal photons, to see a larger population inversion and then stimulate the emission process. However, a large number of photons that are coming in would also start to deplete the population inversion faster. Remember, these are dynamic, okay. So that is varying with time. So a larger number of optical photons coming in will start to deplete the population inversion, and the gain is basically a function of how much the population inversion is there or has been created. That population inversion, as it drops, the gain also starts to drop. In addition, the gain actually decreases and starts to decrease, reaches a certain maximum value, certain optimum value for a certain optimum length of the fiber. Okay, so if you start increasing the length of the erbium doped fiber, then the gain initially begins to increase, and then after a certain value, which is optimal length, the gain starts to decrease. Again, the reason being that as the gain starts to increase, the pump power that you have applied will start to decrease. Okay. So as the pump power decreases, there is not sufficient population inversion, which means that the gain actually starts to drop. So when you are creating a commercial erbium doped fiber amplifier or utilizing the erbium doped fiber for any purposes, it is more or less recommended that you work with the optimum length. Okay. At the optimum length, the gain of the fiber amplifier is maximum. So these are some points about erbium doped fiber amplifier. In optical communications, recently we have started utilizing another fiber based amplifier called as Raman amplifier. The basic idea of a Raman amplifier is very simple. Suppose I take a photon of some wavelength lambda p, and then I have a medium which has which is capable of generating Raman effect. Okay. What is Raman effect? Well, this input photon generates another photon at a wavelength which is a certain wavelength higher. Okay. So, this is called as the Stokes shifted photon. Okay. So, this is called as a Stokes shifted photon, and in optical fibers you can see this effect when lambda p is around 1460 to 1480 nanometer. Okay. The corresponding Stokes shifted photon, which is kind of amplified version, will actually be around 1550 or rather 1560 to 1570 nanometer. Okay. There is almost approximately about 100 nanometer difference. So, you have a shorter pump power, and then that would result in a Stokes wave which is at a larger wavelength or a longer wavelength. Okay. How is this actually useful for us? Well, before you put in a span, you actually have a erbium doped fiber amplifier, correct. Now, to this erbium doped fiber amplifier, just before that you can actually take in this 1460 nanometer pump, okay, and then connect this pump onto the fiber. Notice that this would act as a pump, starts to interact with the signal that is coming in from this side. Okay. So, here is where your signal is coming in from, but as this signal starts to talk to the pump is propagating backward and starts to amplify the signal. So, you actually have a certain amplified signal coming in, which then can be further amplified with respect to EDFA. But the advantage here is that EDFA can be reduced, the gain required for the EDFA can be reduced, and the pump can be remotely used, right. So, this Raman amplifier is actually a distributed amplifier, as we would say. This is called as a lumped amplifier because you have to put it at a particular point, and then compared to the span length, this erbium doped fiber length, which is around 20 to 40 meters typically, is very small compared to the Raman amplifier, whose lengths are typically in tens of kilometers. Okay. Raman amplifier is normally combined with the erbium doped fiber amplifier because Raman by itself is not used for optical amplification purposes. The reason for that is, as the pump power increases, okay, there is a backscattered power called as the Rayleigh scattering. Okay. So, this Rayleigh scattering limits up to what pump power I can actually use, what is the maximum pump power that I can use for the Raman amplification process. Okay. In addition to this, any fluctuations in the pump power is actually felt instantaneously onto the signal as well because of the very fast response of Raman effect, whereas this response time is in milliseconds, whereas for Raman it is in nanoseconds, whereas for erbium doped fiber amplifier it is in milliseconds. Therefore, any fluctuations in the pump power is not typically altering and creating some problems in the erbium doped fiber amplifier. Okay. So, this is about Raman amplifier, which is one of the newer technologies typically made to work in L band, the long wavelength band, which is around 1600 and beyond that one. Okay. In addition to this semiconductor optical amplifiers, I am not going to cover that one in detail except to mention couple of drawbacks of semiconductor optical amplifier. The gain is polarization dependent. Semiconductor optical amplifiers have a very high amount of crosstalk between the wavelengths. However, this high crosstalk is actually quite useful. Okay, you can use this as a wavelength converter. Okay, you can use this as a wavelength converter to convert from one wavelength to another converter. And these days, SOA based optical logic converters or header recognition kind of units are being implemented. These are all made possible because of the fast response time of the semiconductor optical amplifier, a large bandwidth compared to erbium doped fibers. SOAs can amplify signals from 1300 to 1600 nanometer, basically because they utilize semiconductor materials which are transparent to light in this entire region. Okay, so these are quite broadband. Okay, the problem is their gain is polarization dependent and they have a high amount of crosstalk. Therefore, they are not widely used as erbium doped fiber ion amplifiers for communication amplification purposes, but they are widely used in optical signal processing. Many optical signal processing elements actually use a semiconductor optical amplifier. The construction of an SOA is very similar to a double heterostructure laser diode that we actually talked about. The pump is from the current and the pump is in the transverse direction. Everything that we talked about lasers actually holds for semiconductor optical amplifiers as well. In the next module, we will discuss the noise processes that are associated with the optical amplifier and then talk about the improvement that an optical amplifier such as erbium doped fiber amplifier provides to the signal or provides the performance of the systems in optical communication systems. Thank you very much.